Okay, so the topic for this video is waves and the Bohr model of the atom. So just to review what we learned back in the evolution of the atom lesson, Niels Bohr said that, just as Rutherford did, that there was this nucleus with the protons and the neutrons in it, and around that nucleus there were electrons. And those electrons were placed in circular orbits, or they traveled in circular paths around the nucleus. He really had three parts to his model. He said, number one, only orbits of certain radii and energy are permitted. So we talked about the atom is quantized. Those orbits, these rings, can only possess certain energies, okay? And when the electron is in that orbit, it must maintain that energy. Number two, electrons will keep the energy the entire time it's revolving in its orbit. And number three, energy is absorbed or emitted when an electron jumps from one orbit to another. So an electron is able to go from, let's say, a ground state, something close to the nucleus, away to an excited state. Okay? For example, the flame test from Regents Chem, if you put that chemical in the flame, you let it absorb, and the electron absorb energy, and it was able to jump from a ground state orbit to an excited state orbit. Alright, so his proof was the line emission spectrum. I'm going to start by showing just a short little video that kind of explains the spectrum itself, and then we'll relate it back to Bohr's model. I'm just going to click on this and get out of the way.
Energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are four lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transitions shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay, so as was shown in the video, what is really going on is some kind of element, gaseous element, is electronically excited. So we run electricity through it, we can put it in a flame. It allows the electron to jump from a low energy, an orbit that's close to the nucleus, out to an excited state. Okay? It's really unstable. The electron doesn't stay there for a very long time. Eventually that electron will go from high energy back down to low energy. Okay? And there's different jumps it can make. That electron could be in the third orbit, the fourth orbit, and so on. And it will jump back down. And when it jumps back down, it will release some amount of energy. Okay? That specific amount of energy we're going to see in a few minutes corresponds to a specific wavelength or a specific color of light. And when we looked at that hydrogen, we saw the 4 or 5 discrete lines that corresponded to 4 or 5 different energies that were released when that electron made the jump back down to the ground state. This line spectra supports Bohr's theory that electrons can only possess certain energies because as they jump from orbit to orbit, they release those energies that they had absorbed. Okay? So because they only release specific energies corresponding to these discrete wavelengths, it told us that the atom itself, or those electrons, were quantized. They could only possess certain energies. All right? If this were not true, then when those electrons were turned back down to the ground state, we would actually see the entire visible spectrum. We'd see the entire rainbow. Okay? There would be countless of wavelengths that we could see, countless energies that could be emitted when they made that jump back down. So again, just to review, the thing that causes these line spectra are electrons traveling from excited state back down to the ground state. And when they do that, they release energy in the form of light. The important thing about this that supports Bohr's theory is you only saw discrete lines. You did not see that spectrum. okay? So it's very similar to us traveling up or down a staircase. So at each point on these steps, we might assign a certain potential energy, okay? So at the very bottom, I might have 0 joules of energy. First step, I might have 5 joules of energy. Second step, I might have 8 joules of energy. Next step, I might have 15 joules of energy, and so on, okay? So as I'm traveling up those stairs, it's the same thing as going from orbit number 1, which might be step number 1, to orbit number 2, which might be step number 2, okay? And then traveling back down. When a person travels from this step to this step, they can only release or emit 3 joules of energy, okay? If this was the same thing in our atom, 0 joules, 5 joules, 8 joules, when that electron traveled from the third orbit to the second, they would also only release 3 joules of energy. That energy would correspond to a specific wavelength. And if you look, when I make these jumps, there are only certain amounts of energy that could be released, okay? It's not an infinite amount of energy, so I don't see that line spectrum. It's also important to note that when we look at hydrogen's spectrum, there's only a certain part of it that we can see with our eye, okay? And that is known as the Balmer series. So those were like those 5 distinct lines we just saw in that animation. The electrons we already know are traveling from excited back down to ground. But when we see those discrete lines, their final orbit, n sub f, the final principal energy level, is a 2. So it would be like always jumping back down to the second step. They might go from the third step to the second step, and that might be this first line here. They might go from the fourth step back down to the second step, and that might be this line right here, okay? But for that visible spectrum, we're always returning back to the second orbit, okay? There are other energies that are emitted or other spectra that we can't see with our eye from hydrogen. The first one is referred to as the Lyman series, and that would actually occur when the electrons travel back down to the first orbit, like the first step here, okay? And the wavelengths given off by those photons or by the energy released is just outside of the spectrum that we can see with our eye. So it would look something like this, and this is the UV range, okay? And then finally, if electrons travel back down to the third orbit, the third energy level, like the third step in our staircase, that would be the infrared region. So I don't want you to think that what we see with our spectroscopes, that's the only energies or the only wavelengths that are emitted. All right, so there were some problems with Bohr's atomic model. So first, we know protons and electrons are attracted to each other because they have opposite charges. Positives and negatives attract. We also know that electrically charged particles moving in a curved path, like that circular orbit that Bohr hypothesized, should give off energy. Despite this, atoms don't collapse. So if this is actually true, then if electrons are traveling in a circular orbit, they should lose energy and they should eventually spiral in towards the nucleus, okay? Bohr said that didn't happen, but classical physics, or the science at Bohr's time, couldn't explain what Bohr was seeing with that line emission spectrum, or what he proposed to be the model of the atom, all right? Classical physics, as an aside, you'll read this in your textbook, also couldn't explain 2 other things. Something called black box radiation, which is really when hot objects emit a color. So it's kind of like if you have an electric stove. If you turn that stove on really high, the coil will turn from a black color to like a red or an orange color. Okay, classical physics couldn't explain that. The other thing is the photoelectric effect. We're going to talk about this in a couple of videos from now, but it really is when light or energy is shined on a metallic object, electrons are displaced, okay? So classical physics couldn't explain these 2 things as well as the line emission spectrum. So there were some experiments that were done by Planck and Einstein and some other scientists. And it was eventually concluded that energy was quantized. It was absorbed or emitted in multiples of something called hV. We're going to talk about that in a little bit, okay? What we're really getting at is electrons are going to behave like both a particle and a wave. Now we already know from Thomson that the electron is going to behave like a particle, okay? Looking at that cathode ray tube experiment, he saw that ray come out of the cathode, glowed for us. He saw it bend towards the positive magnet, showing that it had a negative charge to it. He could put like a little wheel in between this and it would move it. So that let him know that there were particles hitting the wheel, right? An electron is a subatomic particle. So it does have properties of a particle. But his son, George Thomson, also found that the electron has a wave-like nature. Okay, it traveled through space like a wave. So that gives us this wave-particle duality. The electron must behave both like a wave and a particle. And now with this new construct, we can now begin to explain what Bohr saw with that line emission spectrum and with the black box radiation and with the photoelectric effect. So if this is actually true, if electrons do possess properties of a wave, then we need to know a little bit about waves. So if you've taken physics, this is going to be a review for you. But there are two vocab words that we need to know in regards to waves. The first is wavelength. You'll notice it's a lambda symbol. Okay, it's right in your reference tables. It is defined as the distance between two repeating points on a wave. So if you look at my diagram, like a cosine or a sine curve that you guys have drawn in math, if I pick two adjacent peaks, the distance from each of those peaks to each other is called the wavelength. Okay? The SI unit for a wavelength is meters. So we will be measuring that in meters. Of course, they can be very, very small. You might see them as nanometers, but the SI base unit is a meter. Frequency, on the other hand, is kind of like a V for its symbol. It's really new, the Greek symbol. It's the number of waves that pass through a point in a space each second. Okay? So if I picked a peak as my point, I'm going to count how many peaks will pass through a point in a given second. Okay? As you can imagine, the longer the wavelength, so the bigger the wavelength, the smaller that frequency. Okay? And we'll talk about that in a moment. So electromagnetic radiation doesn't just encompass this visible spectrum that we were seeing with the Balmer series, okay? And actually includes all of this. This is a diagram taken right from your textbook, so when you're reading you're going to see this as well. The visible spectrum is just a small portion of the electromagnetic radiation. It also includes UV, infrared, microwaves, radio waves, and so on. Regardless of what type of electromagnetic radiation we're dealing with, all of it will travel through space at the speed of light. And we notate the speed of light as a little c, and it has a specific value of 3.0 times 10 to the 8th meters per second. This value is highlighted in your reference tables, okay? So if you take a look right behind your periodic table, you're going to see these variables, okay? You're also going to see this formula right here. I would encourage you to star it in your notes. It's an important equation for us. This equation tells us, again, every electromagnetic radiation travels at the speed of light, and that is going to be equal to lambda, which was our wavelength, and nu, which was our frequency. And remember, wavelength is measured in meters, so you can see those units would cancel out. And frequency was measured, I don't know if I stated this in the previous slide, it's measured in inverse seconds, so I'm going to go back, inverse seconds, which is also abbreviated as a hertz. Okay? You can use either of those for frequency. And again, you would see the seconds would cross out, giving us this nice equation. Okay? As I mentioned, the longer the wavelength, the lower the frequency. Okay? So the further apart those peaks are from one another, the more slowly that wave is going to travel. The less peaks are going to get through a point in a given time. Okay? The opposite is true if you have a very small wavelength, okay? Small wavelengths means we're going to get a lot of peaks traveling through a point in a given second. So because these always have to multiply out to that same speed of light, if one of these values goes up, the other one has to go down. They're inversely related, in other words. And as I mentioned, we're going to use this quite a bit with our line emission spectrum. So the next, well, let's do a couple of examples actually. So here we have a math question. It says, what is the frequency of green light, which has a wavelength of 4.90 times 10 to the negative 7th meters? Sorry, I didn't superscript that. So I would strongly encourage you, anytime you're doing a math question or anytime you're calculating something, that you take from the question the variables and you write it on the margin of your paper. So it says, what is the frequency? Well, I remember frequency is that funky looking V, okay? And I don't know it, so I'm going to put a little question mark there. It says it has a wavelength, so that's our lambda, of 4.90 times 10 to the negative 7th meters. Now it's pretty evident what formula we're going to use here because we've only introduced one. But if I was unsure, I could go to my reference tables and I would look for an equation that has these two variables in it. There is only one, and that's the speed of light equals the wavelength times the frequency. Now I know I'm solving for my frequency. I'm given my wavelength, but I can't have two unknowns in one equation. So if you recall, that speed of light is always going to be 3.0 times 10 to the 8th meters per second. Again, right in your reference tables, it's not going to change. All electromagnetic radiation is going to have that value. So all I need to do is substitute into this equation. I know the speed of light is 3 times 10 to the 8th meters per second. I know that's equal to my wavelength, 4.90 times 10 to the negative 7th meters. And that's times my frequency, which I'm unsure of. Okay, that's my unknown. I'm going to isolate my unknown all by itself. So I'm going to divide both sides by 4.90 times 10 to the negative 7th. As I'm doing this, I'm sorry, I'm kind of running out of space, but as I'm doing this, you will notice that I'm including my units and I'm showing all of my work. It's really important that you include your units because now I can see that those meters are going to cancel out. Okay? Sometimes you'll be given the wavelength in nanometers and you'll actually have to convert to meters first before you plug in. If you don't include the units in your work, then you might miss that conversion. Okay, that's needed beforehand. So I would go ahead and plug this into my calculator, 3.0 times 10 to the 8th divided by 4.9 times 10 to the negative 7th, and get my answer for my frequency. When I do that, I got 6.12. Be very mindful of your sig figs. If you look at your two values that you did your calculations with, both of them have decimals present, so think back to Regents Chem. If there's a decimal present, you count from the Pacific Ocean. You start counting at your first actual digit and you don't stop until the end. So that's 1, 2, 3, sig figs here. And then decimal point present, start at the first actual number, 1, 2, 3 sig figs here. So my answer has to have 3 sig figs, which I have right now. It'd be 6.12 times 10 to the 14th inverse seconds, or hertz. Now if I went back to the previous slide, I would see that is the unit for frequency. So I'm in good shape with my calculation. Alright, so that's one example. Let's do a second one before we move on to our next formula. Second example says determine the wavelength. So already a little different. Wavelength, remember, is that lambda. That's my unknown. It says if my frequency, so that's my little funky V, 3.5 times 10 to the 9th hertz. Now I like to write hertz as inverse seconds because again I can see my units cancel out. That's my preference. It's up to you. I know from my reference table that there's only one formula that relates the two, and that's the speed of light equation. I also know that the speed of light is always for me going to be 3.00 times 10 to the 8th meters per second. So now all I have to do is plug into my formula. I know the speed of light is 3.00 times 10 to the 8th meters per second. I know that's equal to my wavelength, which is my unknown, times my frequency. 3.5 times 10 to the 9th inverse seconds. I'm going to isolate my lambda, or my unknown, all by itself. Oops, didn't mean to write that. I'm going to isolate it by dividing by my frequency. So these are gone. And then 3.5 times 10 to the 9th, 1 over seconds. Again, you'll notice my units. I can see that the seconds are going to cross off, leaving me with meters. That's good news because my wavelength is supposed to be in meters. So I go ahead and I plug this into my calculator and I get 0.0857. So this is actually incorrect. If I look at my sig figs, I have 3 sig figs here and I have 2 here. So I'm going to want to round this to 0.0. First 0 doesn't count. I count from the Pacific Ocean and I don't start counting until I reach my first actual digit. 0 is not a digit, so I'm going to do 8, that's my first sig fig, and then 6, that's my second. And there's my answer. Okay? So again, star this in your notes. That's a formula that you're going to need to be able to use. The second big formula that you need to know, I would star this, it's right in your reference tables, you need to be able to use it, is the energy of a photon, okay? So the energy of a photon, the energy released when an electron makes a jump from excited back down to ground state, is equal to h, which is a proportionality constant. This was found by Planck, that's why it's his constant, and just like the speed of light, it's always going to be 6.63 times 10 to the negative 34th, and the units, I forgot those, are joules times seconds. Again, right in your reference tables. And then that V is still my frequency, and that is inverse seconds over hertz. Now, Planck found that energy was released in discrete chunks while studying that black box radiation. So because it was released in chunks, that means it's quantized. It has a proportionality constant, which is this guy right here, okay? So energy is released in multiples of this very, very small number, 6.63 times 10 to the negative 34th joules times seconds, okay? That's kind of strange that we see energy being released all the time, and it's not like a strobe light that we see, okay? This is such a small number that we really only see that quantized nature showing up when we're dealing with really small things like the atom. Okay? Something macroscopic like us, if we lose energy, it doesn't appear to be lost as chunks. Okay? It would be like a millionaire or a billionaire losing a penny. They wouldn't notice it as much. Okay? Whereas that small little atom, we're going to start to see that quantized nature show up a little bit more. All right? But again, this is an important equation for us. Let's do some practice. So the first practice question says, determine the energy of a photon. So I need to know the energy of one photon, that's my question mark, if the frequency is equal to 3.5 times 10 to the 9th hertz or inverse seconds. And again, if I wasn't sure what formula I would be using, again, this is the example to E equals HV, so we know which one. But I could check my reference tables. There's one that's going to have both of those variables, and that's the energy of a photon equals Planck's constant times the frequency. H is not given to us in the question. It's not going to be given to you. It's right in our reference tables. That's 6.63 times 10 to the negative 34th joules times seconds. And I can just plug in what I know. I don't know my energy. I know my H is 6.63 times 10 to the negative 34th joules times seconds. And I know I'm multiplying that by my frequency. This frequency only has 2 sig figs. So when I go ahead and solve for my answer, I'm only going to express it to 2 sig figs. And I would go ahead and plug this into my calculator. When I do that, I get 2.3 times 10 to the negative 24th. My seconds cancel out, and I'm left with joules, which would be the SI unit for energy. Okay? So here's my answer right here. Now, for the second part of this example, I'm going to take that same information. So I'm going to take that same frequency, 3.5 times 10 to the 9th hertz, or inverse seconds. I've already calculated the energy of one of those photons. Let me copy that back down. It was 2.3 times 10 to the negative 24th joules. Okay? But in this question, it's asking me what is the energy in kilojoules per mole. This is the energy in joules per one photon. So this is a different type of question. It's not plugging into the formula. Okay? We've already gotten the energy answer. What we need to do is manipulate the units. I'm in joules, I want to be in kilojoules. So you might remember back in Regents Chem, we did this given times want over have. It's essentially dimensional analysis. That's what we're going to do here. We want to set up some type of fraction that's going to get rid of the joules and leave us with kilojoules. So anytime I want to get rid of something, so I want to get rid of the given, I have to put the same unit kitty corner to it. And I want to be left with kilojoules on top. So I need to know some kind of relationship between these two things. I know 1 kilojoule is 1,000 joules. Now, unfortunately, that's not the end of it. That gets rid of my joules and leaves me with my kilojoules, but I also have to have moles at the bottom of my fraction in the denominator. So I need to know one more conversion factor, and you might remember this from Regents Chem. 1 mole is equal to a specific value. That's 6.02 times 10 to the 23rd atoms or molecules, or in this case, photons. So again, I want to get rid of photons. I'm going to go ahead and set up a second fraction. I need photons at the top, right, kitty corner, to get rid of them. And I want moles at the bottom. That's my 1. It's just at the bottom this time. And I'm going to place my numbers in with the units. 1 mole is equal to 6.02 times 10 to the 23rd. This number, Avogadro's number, is right in your reference table. So again, all you need to do is be able to use or locate those values on your periodic table. And when I do that, I should get something similar to, I didn't round this in my work, so it might be a little off from what you get. I get 0.0014. Again, I'm only allowed to express 2 sig figs, and this is kilojoules per mole. Okay, so just a little twist on the energy of a photon. So again, those 2 formulas are really, really important for us to understand. Now, I'm going to give us some additional information that's not in our reference table in a moment, but just again to remind you, we're really building off of this line emission spectrum. So what's going on to get each of these discrete lines is electrons are traveling from a high energy level back down to, in the visible spectrum, the second orbit, the second energy level, okay? And that energy that's given off, I can now relate to a frequency, and then once I know my frequency, I can relate it to a wavelength, and that wavelength will correspond to a specific color of light, okay? I'm going to go on a little bit more, and I'm going to talk about, well, how can we figure out if that electron travels from energy level 1 to energy level 3, or energy level 4 to energy level 2? How much energy is either released or absorbed? So you may remember this from honors chemistry if you took it. We can technically determine the energy of an electron when it's in any of those orbits for the hydrogen atom by using this equation right here. This one's not in your reference tables. It is negative 2.178 times 10 to the negative 18th joules over n squared. And in this case, n is standing for our principal energy level. So if we're in shell number 1, n is going to be equal to 1. If we're in shell 2, n is going to be equal to 2, and so on. Okay, all the way up to 7, because that's how many energy levels we need for any atom in the periodic table. All right, so if I'm doing some practice with that, if I want to calculate the energy of an electron in principal energy level 6, I can just go ahead and plug into my equation. The energy of an electron, n, is equal to 6. I'm in the 6th shell. The energy of an electron is equal to, just getting my work out here, negative 2.178 times 10 to the negative 18 joules all over n squared. In this case, I'm dealing with 6, and I'm going to square that. I just plug it into my calculator, and when I do that, I get negative 6.05 times 10, 50, times 10 to the negative 20th joules. Okay? Whereas if my electron was in the first principal energy level, now my n is equal to 1. I plug in negative 2.178 times 10 to the negative 18 joules all over 1 squared, because my n value is 1, is going to give me that same value, negative 2.178 times 10 to the negative 18th. Essentially, this is telling me how much those staircases are worth, how much energy. So when an electron jumps from stair 3 to stair 2, or from stair 6 to stair 1, I can figure out how much energy is released, and then I can correspond that to a frequency and then to a wavelength, okay? So let's do our last little part to this. As I mentioned, that first equation is telling me how much energy each of these steps are worth. I can now use that to figure out if I jump from one step to another or from one orbit to another, how much energy is released or absorbed. So I can calculate my delta E. Anytime you see that delta symbol, it means change in. So I can calculate my change in energy by doing my final energy level to my initial energy level. Okay? It's just like if you were doing a change in volume, it would be your volume final minus your volume initial. That delta is always final minus initial. So if I go back, what if my electron is traveling from n equals 6 to n equals 1? Well, if you recall, we just calculated how much energy an electron possesses in the 6th energy level, the 6th step, or in the 1st energy level, the 1st step. Okay, and I'm just going to recopy those down from our notes previously. The 6th energy level was negative 6.050 times 10 to the negative 20th joules, and the 1st was negative 2.178 times 10 to the negative 18th joules. All right? So if I want to figure out how much energy is lost, it's always E final minus E initial. So my final is 1, and my initial is 6. So I plug in what I know. The energy at orbit's final orbit 1 was negative 2.178 times 10 to the negative 18 joules minus E initial. I'm starting at negative 6.050 times 10 to the negative 20th joules. Again, I just plug that into my calculator, and when I do, I get a negative. This tells us energy is released. That makes sense. It's going from excited, something further from the nucleus, to a ground, something closer to the nucleus. And it's negative 2.118 times 10 to the negative 18 joules. Okay? Negative tells me I'm losing energy, and this is how much energy I'm losing. All right? I could relate this energy to the frequency of that wave using this equation right here, and then that frequency to a wavelength using this equation here. And I could actually figure out when this transition is made where it shows up on my spectrum. Okay? I could see if it was infrared, UV, and what the exact wavelength is. And this is some of the practice we're going to be doing in class next time. Okay? But the important thing that you take away from this is that, again, those electrons can only possess specific energies when they're in that orbit. Okay? All right, we'll see you in class.